vector field, and the vector field is 1, comma, y. And I want to find the line integral along this path here, this red path from, oh, let's just say this is 8.720 to 0, comma 8.72. My favorite number today, 8.72. Okay, so how am I going to find this line integral along the red path from 8.720 to 0, 8.72? How am I going to find that? So let's see. I could do it in red. So I want the, let's call this C. So let's talk it through. How can I find that line integral along the path C through this vector field F? Any ideas? Yeah, Anna. Okay, why is it going to be the same value? Okay, so is this a conservative vector field?
Yes.
Yes, therefore that line integral equals? I can do the circle, right? I could do the circle. Is that it? Any other ideas? Yeah, Cody.
We use the fundamental theorem of line integrals too.
And what would that say?
That says that line integral should equal the function evaluated at the endpoint minus the function evaluated at the endpoint.
So if we had a potential function, we could evaluate it at 0, 8.72.
Let's subtract that from the potential function of 8.72 times 0.
What do you guys think? The rest of you. Agree? You're going to make it. Right? Yeah, the final value of the potential function minus the initial value of the potential function. Okay? What else? Those are the only two ways to get this? Yeah, go ahead.
Do a straight line from
Yellow doesn't show up on the, how about light brown? So from where to where?
from 8.720 to 0, 8.72.
So I could actually do a line integral along that path. Call it C2. Well, yeah.
I just want to make sure, when you did the final minus the initial,
Mhm.
is it f of 0, comma 8.72 minus f of 8.72, comma 0?
So what's the final, where's my final point here? Oh yeah, right. I just rewrote the same thing twice. Thank you. Yeah.
You make it again?
Oh, I'm going to make it easily this time. You can even see the whole right parenthesis. Is that better? What else? Can I just do this line integral? can just do this directly, right? So you can just do what I asked you to do. So you have to parameterize that, looks like a parabola, parameterize that parabola, and calculate that line integral. We could find the parameterization of this line segment and do that integral. We could parameterize the quarter circle, do that line integral. We can use the fundamental theorem of line integrals. And then there was another easier path, right? Any path, right? Any path from here to here is going to get us that. Okay, so now I want to get the value. What's your choice? Path of least resistance. I agree. So what do we need? Potential function. What's the potential function? X plus y squared over 2 plus c plus any constant. Check it. Partial with respect to x is 1. Partial with respect to y is y. Got it. Therefore, line integral equals, which would be, so
8.72 squared divided by 2.
that would be our f of 0.72, and then, think I'll make it? So that's a perfectly legitimate way to express the answer. Is it uncomfortable? It shouldn't be uncomfortable. If it is, so that would be the value of the line integral that the original one I asked about, okay, by the fundamental theorem of line integrals. Any questions? So what might this be calculating, like in context, right? So in a context, what might this value be calculating?
Like an application setting?
Yeah. What was the one that we talked about?
The one where we had a gravity field and it was pushing down on...
But this is a two-dimensional field, and it's not the gravity field. So what did that calculate?
Could be magnetism.
Okay, but that's not a quantity. What quantity?
Work done by the field on an object moving along that path.
Yeah, if this is a force field, right? So if this is a force field, then it's the work done by the field on the object as it moves that path. So it's the work done by F. And that's in the horizontally. But really, there's another meaning for this that relates. Where does the potential function live? Does the potential function live in R2? Where does it live? R3. So,
It's a difference in height.
okay, good, right? So let's see that. So really, in the context of the fundamental theorem, right? This is a gradient field for some surface, right? What surface? What surface? Oh. X plus y squared over 2, right? So really, we could think about these paths as paths on from the point in R3. So again, Those were those paths like that. But now in R3, what does this value represent then? If it's f of 0, 8.72 minus f of 8.72 comma 0, yeah, that's really what about the z-values?
They're different.
The difference, right? So it's like what Michael said, right? It's really the overall net change in height. So that line integral equals the change in height of those, the change in z of those 2 points. So rather than accumulating little bits of work, so another way to think of this, rather than these accumulating little bits of work in the gradient field in the xy plane, you can also think of it as accumulating little changes in height of the potential function from the lower one to the upper one, because this is higher up. So this could be work done in the plane, but it's also the change in height. It's the accumulating changes in height from one point to the other. Okay, any questions on that? Lots of cool conceptual stuff going on there. So in a conservative vector field, let's summarize in a conservative vector field. Can I erase and go on? Any questions? So here's a summary. Make sure if you're going to try to copy this down that you're listening and engaging your mind, not just copying words. You can always go to the video and get your notes to look pretty later, okay? So here, for conservative vector fields, the following statements are mathematically equivalent. If any one of these is true, then all the rest are true. These are all equivalent statements. So given one, all the rest hold two. So F is a conservative vector field, okay? If F is a conservative vector field, then F is a gradient field, meaning it has a potential function F such that the field is the gradient of F. What was another thing we said about conservative vector fields? Before I list them, let's just brainstorm. What were they? What's that? We get path independence. What else? Good. What else was true? All circulations are 0. Every circulation integral is 0. What else?
They pass Clairaut's theorem.
Clairaut's theorem holds. And then there's one more thing.
It's the difference of heights.
Okay, so what is that? Yeah, where does that come from?
Fundamental theorem of line.
Yeah, the fundamental theorem of line integrals holds. Good. Okay, so Clairaut's theorem holds. Every closed loop is 0. F is path independent for given any 2 points A and B. You have a constant line integral from A to B, and then the fundamental theorem holds. If C is a path from A to B, then the difference of the potential function is the same as the line integral. So if any one of these is true, then all the rest are true. If any one of these is true, then all the rest are true. Okay, questions about conservative vector fields? All right, let's move on. Let's talk about Green's theorem. Okay, so here's Green's theorem. Suppose that C is a simple closed curve. Simple means it never crosses itself. Closed means it makes a loop, like circulation. So if C is basically if C is a circulation loop, and it surrounds a region D in the plane, oriented so that the region is on the left as we traverse the curve. Okay, we'll talk about that later. Suppose that we have a smooth vector field defined everywhere on C and in D. So here's all the setup for Green's theorem. And so then this is what Green's theorem says. Green's theorem says that the line integral around the boundary of this thing is the same as the double integral of the partial of q with respect to x minus the partial of p with respect to y over the region inside C, D. So let me just draw a little sketch here. So here we are in R2. We've got some path. So we're in a vector field, and that's PQ. P is the x component of the vectors. Q is the y component of the vectors that makes the vector field. So, and then we're going to do a loop around like this. So C is the path around, and then D is the region that it encloses. Better. So the orientation means which way would we walk around on this C so that the region is always to our left. And we'll talk more about that later. But so I can walk around counterclockwise or clockwise. If I'm walking around, which way do I walk around so that the interior, the D region, is to my left? Counterclockwise way of drawing it, right? So if I'm walking around counterclockwise, then the region is to my left. And we'll talk more about that. But that's what we mean by the orientation of this. If you make it the other way, then these will be equal and opposite. Okay? These integrals will be equal and opposite if you go around clockwise. Okay, so how does this relate to the Calc 1 fundamental theorem equation? How does this relate to the Calc 1 fundamental theorem equation? So what was the Calc 1 fundamental theorem? Integral from A to B of, so let's use G because we got some F's up here. So I'll use G of x dx equals some other function G of B minus and what are some qualities of that? We have what? We have, how does little g relate to big G? Derivative, right? Little g is the derivative of big G. We're integrating across an interval, and in order to use the fundamental theorem, we only need what? Like the endpoints, right? So we can just evaluate the antiderivative at the endpoints, and that gives us the same result as accumulating bit by bit from one endpoint to the other, right? So we're on the left side, we're accumulating bit by bit from A to B. And then on the right side, it's like all we need is the actual function value at B minus the function value at A of the antiderivative to calculate the same thing. So this side is accumulating bit by bit using the rate of change, right? Using the rate of change. This side is basically looking at the total net difference of final minus initial of the function. So this is essentially a fundamental theorem. So we want to relate this. How can we relate this to all these things we're talking about here in our fundamental theorem? So let's go check something here. Okay. So we said the accumulation of many bits of a quantity, right, using the rate of change is equal to the final value of the function minus the initial. So here I'm using rate of change of f and f. So how do these match up? Do they match up? Does the right match up with the right and the left match up with the left? Or do they match up crisscross? Does the right side on the top match up with the left on the bottom and vice versa?
The left goes with the right.
He wants crisscross. What do you think? Agree with that? I see some nods. Yeah, right. Okay, so the accumulation of many bits of a quantity is this in both cases. And those bits are calculated using rate of change, right? So where do you see, we know this is rate of change of f. How do we see rate of change here? Yeah, so these are derivatives, right? So this is what the partial of this with respect to x. And this is the partial of y. So this is some sort of derivative, right? It's some sort of rate of change. Each calculated by rate times change in independent, right? Is equal to the net change of the quantity, in both cases associated with the boundary, right? So this is like, and this, it's a to b is like the inside of the interval, and d is like the inside of the loop. See that? So from a to b is across an interval, and d is within the loop. And then, so then B and A are like the boundaries of the interval, right? Like the endpoints of the interval is like the boundary. And C is the boundary of D. Do you see that? So there's lots of parallelism here. But we've stepped it up an order of integration. So now a double integral can be of computing bit by bit over the interior is equal to a single integral around the boundary. Okay, any questions on that? So Green's theorem is a version of the fundamental theorem. And we have the fundamental theorem of line integrals too. So now you know, or at least you've been introduced to, 3 fundamental theorems. The original fundamental theorem of calculus, the fundamental theorem of line integrals, and now Green's theorem is like an offshoot of that. It's like looking at in vector fields, right? Yeah, we'll see that later. Yeah, that's the right question. I haven't shown you that yet. But we'll get into that later. But just for now, just know that this is essentially some sort of derivative of capital F, whereas this is the derivative of little f. So that's all you need to know for now. Okay, so the proof of this, I'm going to just mention a few things of the proof of Green's theorem, but we don't have time to really work it out. So here's the idea. We've got, we're going to partition up the interior of C. We're going to partition up D into, so we're not going to do the proof of Green's theorem, but what I'm choosing to talk about now is very important, okay? I'm going to partition up D into little elements. And we're going to sum up a bunch of little circulation integrals for each element. So the circulation of f around small curve, we're going to sum up each circulation of f. We're going to sum all those up. Okay? And then what happens when we do that? So notice, if I do this circulation integral like that, and I add this circulation integral like that, what do you see happens? Yeah? So double counting. So there's this. What's that? Yeah, so in this circulation integral, I'm going to integrate along this path from here to here. In this one, I'm integrating from here to here. So then what happens to those shared edges? Yeah, they're equal and opposite. So when we add up all the circulation integrals, we add them all together, we're just going to get what in the end? Yeah, so only we're going to get 0 for all the shared sides. So which ones are not shared? On C, right? So all those little segments along actually C are not shared, and so but all the interior shared sides are going to cancel out. So all shared sides of the elements sum to 0, leaving only the sum around the boundary. So this is one way to look at summing up the circulation integrals of all the elements in D. Another way to look at that is actually do it. Okay, so actually do each circulation integral and sum it up, and this is where things get a little complicated. So we're not going to go through that. But what happens is when you actually sum up all of those circulations around C, you land here with a double integral. So you're integrating over the whole interior region D. When you sum all those up, you get the double integral of qx minus py. Again, not going to take the time. I'd love to sit down in my office and kind of flesh that out with you if you want. But it all comes back to two ways. This theorem comes to two ways of calculating, summing up all the circulations about all the little elements in D. You get the cancellation effect, and it gives you the circulation around the outside. And then if you actually do it and brute force it out, you can show that you get this double integral of qx minus py over the region. So that's why those are equal. That's Green's theorem. Okay, so that's kind of a very skeletal outline of the proof. Any questions on that?
This is the easy version?
What's that?
This is the easy
Skeletal version.
What do you mean by that?
I didn't show you the proof. I just talked about what it's in the. I just talked about the structure of it. The overall picture. Okay, so let's do examples. So what would it mean to verify Green's theorem? So it says verify Green's theorem if the function is y and 4x, and C is a triangle from 0, 0 to 2, 0 to 2, 4 back to 0, 0.
Would you ensure that the single integral of the region C of f dr is equal to the double integral of region D qx dr?
Right, so and then how do we do that? How do we ensure that they're the same? What would we have to do to ensure that? Yeah, we got to do both, right? So you're gonna actually do the single integral. So our circulation we're actually going to calculate the circulation integral, and we're going to calculate the double integral, and we're going to show that you get the same value. Okay, so from 0, 0 to 2, 0 to 2, 4, back to 0, 0. Okay, so this is just putting together, in terms of solving this problem, it's putting together lots of stuff we've learned in the past. You've got what? You've got partial derivatives, you've got circulation integrals, so line integrals, you've got double integrals. Got to do all that stuff. So see how much progress you can make while I take attendance. So you do as much as you can, and you're either making progress or you're getting help, right? Making progress or getting help. So you're verifying that this statement is true for this particular setup. Okay, check, see if you agree. So don't forget how to do line integrals. We have to keep doing them the rest of the semester. So that like it's been a typical case in previous semesters where there's like kind of like a half a week or a week break of not doing line integrals, and then all of a sudden we forgot how to do line integrals. So you're going to need them at the end. Okay, so make sure you're parameterizing the curve, and then f, right? F is going to be your vector field written in terms of your variable. So you use your parameterization to rewrite f. And dr is the dx dt and dy dt, and then the dot product. So any questions? So adding together the three legs of the line integral, you get 12. And then double integral, partials are 4 minus 1, qx minus py ends up being 3. And then you can do what? Type 2, type 1, type 2 are polar, right? Double integral. So I did type 1, integrating from 0 to 2x, and then accumulating from those from 0 to 2. Good? And we got the same thing, right? There's another way to do this. There's another way to get 12. Anyone discover that? Why?
Isn't that the same thing as taking the integral of the double integral with respect to 1 times the when that goes to area?
Was that the double integral we have? Do we have a double integral of 1?
No, it's technically 3, but it's still a constant. It would still work.
So what can we do?
Okay, turn it into a triple integral.
Divided by 3.
Divided by 3?
Or multiply that by 3, I guess.
Right, so isn't this the same as if you have a constant? Isn't this 3 times the double integral with 1 as the,
So it's 3 times the area.
which equals 3 times area of D. Right, the double integral over D will actually give us area, will give us the same value as area when your integrand is 1. So if your integrand is 3, then we can just take 3 times the area of D. What is the area of this? So this is 2, right? 2 times 4. So 3 times the area of D is 1/2 base times height equals. Pretty cool, huh? So if you recognize when you got to this side, you can say, oh, I can just pull the 3 out in front of my double integral, and then I could do that's double integral will be the same as area of D. So we can do the area of that triangle. Did you catch it? But what do double integrals find? What kind of value does double integral find? Net volume, difference of volumes, right? Net volume, difference of volumes, signed volume. But we can trick it into finding an area for us if the integrand is 1. Then the volume is the same as the area of the base, right? Any questions on this example? So verifying a theorem means you got to do the most work, right? You have to compute one side and compute the other side, and show that they're equal. It's kind of like a proof. But it's not a proof of Green's theorem, but it's showing that Green's theorem holds for this example. So you have to do both sides and say that they're equal. Any questions on that? Okay, another example. So I think this is from your last review sheet, right? Did you remember this from your review sheet? So this says, find the circulation line integral if C is the simple closed path shown through the vector field 1, comma, x. So we've got this part of the parabola and this horizontal line, and then this segment here, this diagonal segment. So we need to find the circulation line integral. So how do we do that? What do we have to do first?
We have to take the partial.
We want to find that line integral around that closed loop. What do we have to do?
We can use Clairaut's theorem to test if it's a vector field here, because it is a closed loop. To me, that kind of looks like a gradient field, just based on the equation. Double integral. The area cannot deal with that.
So how are we going to do this? How do we find the line integral? We have to parameterize which curve? Okay. Right? So we're going to have to parameterize the parabola and find that line integral. Parameterize that segment, find that line integral. Parameterize that segment, find that line integral. Yes? What's that? Can we do Green's theorem? It says that it equals what? Double integral d. Close. You just learned it 10 minutes ago, so I'll let you off the hook. Qx minus py. Yeah, you get the right idea. Yeah. So we can use it. All it said was find the value of the integral, right? That doesn't necessarily mean that you have to compute it directly, right? With theorems, there's an indirect ways sometimes to calculate the same thing. So by finding this, we will have found the same thing as if we had actually directly computed the line integral. All right, so how do we do that? What's q of x? Q of x is 1. What's p of y? 0? Okay, so what's that? So dx dy or dy dx? Type 1 or type 2? Let's do dx dy because we can get away with 1, right? So if we do dy dx, we'd have to split it up into two double integrals because of the bottom boundary. See that? The bottom boundary would cause us to have to do two double integrals if we do dy first. So we're going to do, if we do dx first, we can get away with one integral. So that means we need this and this in terms of x. Notice anything about the integral? So can we just find the area?
Yeah.
Yeah, go for it, right? What do you got?
Well, you just take the area of the triangle on the left side.
Okay.
The side is 1/4 of the circle.
Y equals x squared, 1/4 of a circle?
Got it.
It's a parabola, right? So it's not circular. So it looks maybe circular, but it's not, right? It's this parabolic curve. It's not circular. But yeah, right. If this were a circular curve, you could do that, but we can't. So we're forced to do the double integral here because we don't have a formula for parabolic areas. So x is going to go from what to what? Negative y to root y, right? Because if y equals x squared, then x equals root y. So we're going to go from negative y to root y, and then from 0 to 1. We got it. So it's going to be, is that root y plus y? Because I'm going to get antiderivative as x. It's going to be that minus that. So it'll be root y plus y. And then we'll get 2/3. Doing the math right? Is that 5/6? I tend to remember that that's what that is. Yes, 7/6, sorry. And then we can say, oh, but 7/6 is also what? Yep, this area is 7/6. Just because, nothing to do with Green's theorem, right? That has nothing to do with Green's theorem. It's just the double integral that turned out to be integral of 1 in this particular case then tells us that that area is 7/6. Okay, as you're packing up, so let's go around this. As you're packing up, just watch. So here's this vector field, 5x to the 4th plus y squared 2yx. And here's this ellipse, the slanted ellipse, x squared plus 3xy plus 4y squared equals 1. So do we want to, so if it says to evaluate the line integral, you got two choices, right? You could do it directly or use Green's theorem. What about directly?
Directly would be better.
Oh no, it would be awful, right?
Yeah.
All right, so what about Green's theorem? So now how about doing Green's theorem on this? Double integral of this.
Terrible.
Is it a gradient field?
And so what? Yeah.
0.
So if it's a gradient field, qx is 2y minus 2y. Therefore, what's the line integral? 0, because it's double integral of 0. So this equals 0. Let's see, phew, right? So what's the point of so Green's theorem in a conservative vector field? It's trivial, right? So Green's theorem really is only interesting in non-conservative fields, because if you're in a conservative field, you have a loop integral, which means 0 around a loop. And your double integral would be 0 too, because you have Clause's theorem, right? Those are equal in a conservative vector field. So 0 equals 0, and it's kind of a useless case. Except in this, it's a very useful case. This has just made our life very nice and easy.